Okay, let's do a quick review of mechanical energy. And we know mechanical energy takes the form of potential energy and kinetic energy. And we're just going to do a quick review of what those terms mean and how they can be identified in your Rube Goldberg machine. So energy is the ability to do work. We'll come back to that in just a second. Energy includes potential energy, which is the energy associated with position. And the energy, kinetic energy, is the energy of motion. Energy can be transformed but never created or destroyed. And work measures the force acting over a distance. And work is so the two types of mechanical energy. We're looking at our gravitational potential energy, aka stored energy, and kinetic energy, aka energy in motion. And so let's take a look at potential energy. So to solve for potential energy, you take the mass of the object times the gravity of the planet it's on, so in this case Earth, times the height of the position. So mass times gravity times height, and that gives you potential energy, which is measured in joules. And to solve for kinetic energy, you're going to take 1/2 times the mass of the object times the velocity of its motion. And you square the velocity. Don't forget to only square velocity. And you measure kinetic energy in joules. And mechanical energy is the sum of potential energy and kinetic energy. So taking a look at this diagram, we can see that work is applied on this cart to get it up to the top of the roller coaster. At this height, in this case, it is stopped. So the kinetic energy is 0. All of that cart's energy is in the form of potential energy. Once that car gets moving, the potential energy is transferred into kinetic energy. And at the lowest point of this track, all of that potential energy has transferred into kinetic energy, and it's now going the fastest that it can go. Keep in mind that kinetic energy and potential energy are added together to equal mechanical energy. So the total mechanical energy from the starting point of this cart and all the way through the track has to be the same. We're assuming that there's no outside forces acting on it, there's no friction or air resistance, and that energy is conserved. For your Rube Goldberg machine, you'll see energy transferred between potential energy and kinetic energy in a different way than what you might see on a roller coaster. So let's take a look at this video. We'll skip ahead. These students explain the different interactions of their Rube Goldberg machine. But if we skip ahead, we can see them put this machine into action. So that car started at the top of a ramp. It had potential energy, and once it started moving, that potential energy transformed into kinetic energy, and the kinetic energy transferred between objects. So it goes from car to dominoes, dominoes to ball, and then the ball fell into the cup and turned that light on. So whenever you're building your Rube Goldberg machine, try to think about how is energy being transferred between objects, or how is it being transformed from potential energy to kinetic energy. Okay, so we are going to work through an example problem that you can find on your practice packet. So follow along with this concept and how we do this practice. Okay, so we have a skater, and he starts at the lowest point, and he has some kind of energy already. He's in motion. So we know he has kinetic energy. He's at the lowest point of his path. So this is the lowest point of potential energy and most likely the highest point of his kinetic energy. So to get started, let's solve for his potential energy. We know that he's at a height of 0. So to solve for his potential energy, we take his mass times gravity times height, substitute in those values, and we have a mass of 60 times gravity, which is 9.8, times his height, which is 0 meters. So he has 0 joules of potential energy right now. So we can fill in that blank. And next we're going to solve for his kinetic energy. And we use the equation 1/2 times mass times velocity squared. We substitute in our values, so 1/2 times the mass of 60 times his velocity, which is 8 squared. Do 8 squared first, multiply that by 60, multiply that by 1/2, and we get a value of 1,920 joules for his kinetic energy. And the last blank for this problem is his mechanical energy, and the mechanical energy is just the sum of potential energy and kinetic energy. So that is a total of 1,920 joules. Now don't forget that due to the conservation of energy, this mechanical energy is going to be the same for his whole path. We're assuming there's no friction, no air resistance, nothing, no outside force affecting him. So his mechanical energy will be the same along his path. And we can fill that in for each of these. So he has a total mechanical energy of 1,920 joules across his whole skate path. All right, next up, let's solve for the second set of equations here, or the second set of blanks. We know he's at a height of 1 meter, so we can solve for his potential energy first. Potential energy for this part of his path will be his mass times gravity times height. So 60 times 9.8 times the height of 1 meter. And that gives us a potential energy of 588 joules. Once we fill that in for our blank, we can go ahead and solve for kinetic energy. Remember that he has a total mechanical energy of 1,920, and 588 of that is in the form of potential energy. So that leaves us with 1,332 joules of kinetic energy. And using that amount, we can solve for how fast he's going. So we want to rearrange our kinetic energy equation to solve for velocity. And after it's rearranged, that gives us the square root of 2 times kinetic energy divided by the mass. We substitute in our values. So 2 times 1,332 divided by the mass of 60, and you square root all of that. That gives us a velocity of 6.7 meters per second. All right. That makes sense. He started off at 8 meters per second, but as he starts to get higher up and that energy is transformed into potential energy, his velocity should be reducing. Okay, at number 3, we're assuming he's at the top of this path. This is as high as he's going to go, and he stops right before he starts to come back down. So that tells us that his velocity, if he stops, is 0 meters per second. If his velocity is 0 meters per second, that means that all of that kinetic energy has transformed into potential energy. So he has a kinetic energy of 0 joules, and all of his mechanical energy is now in the form of potential energy, which is 1,920 joules. So now we can figure out how high he is if we rearrange our potential energy equation to solve for height. So to solve for height, we take potential energy and we divide it by mass times gravity. So when I sub in those values, 1,920 divided by 60 times 9.8, I realize he's at a height of 3.27 meters. And now we have solved for all of those blanks. So continue to do this practice set of problems on your own. Keep in mind that at the lowest point of the path, you have no potential energy. All of your energy is in the form of kinetic energy. And at the top of the path, at the highest point, all of your kinetic energy will be in the form of potential energy. And then it's kind of like a puzzle to solve for the variables in between. Reach out to your physics teacher if you have any questions.